Okay, thank you. First of all, thanks for the organizers like Vidyut and Vishal for inviting me here. It's an excellent lecture series going on. I'm glad to be a part of this. This is not exactly the lab session. I would like to introduce you to the NWP models that especially at NCMRWF, what we are doing, what kind of models that we are having, and how the models can predict this or represent this moist convection in numerical weather prediction models. And then I'll go for one or two examples. One example I will show you where the models can go wrong. When you do that exercise, you can understand where the models can go wrong really. So the title of my talk looks very generic, like, I'm not talking about all NWP models. I'm just maybe the medium range weather prediction model that NCMRWF is having. That is called a unified model from the Met Office. So I will be discussing more about that model. So those who don't know me, I'm Mohan from NCMRWF. I'm scientist E. Did my postdoc at IPRC. Then as a scientist, I joined at NCMRWF in 2020 during COVID lockdown. And then working as a scientist there, my expertise on tropical meteorology and subsystem predictability. Currently, I'm working with the global model, deterministic model, and then global model convection with more specialized on the process-oriented diagnostics. So I'll divide this talk into three parts. First, I would be discussing about the moist convection in NWP model, that is the UA model. Then we will see how to evaluate the model apart from the conventional skill scores. What else we can do that to evaluate the model physical component, and then a simple exercise or a case study. So, like I said, NCMRWF model system, we have this, you can see the schematic diagram on the left-hand side, the globe. The blue color shows the operational models. Since we are an operational center, we have a suite of models, starting from the global deterministic, which is 12 kilometers, which gives a forecast for 10 days, it's a medium range scale. And then the same model dynamical core is used, and then it was reduced to a regional model, which is having a 4 kilometer explicit convection. The global deterministic is a convective parameterized, so mass flux convection scheme. And then the regional model 4 kilometer is explicit convection. Then we have a 330 meters fog or chemistry model, just to over the hilly regions of northwestern parts of India for the fog and visibility prediction. Then we have the ensemble of this 12 kilometer. We have 22 member ensemble, and then another 22 member ensemble at 2 cycles, 0 UTC and 12 UTC we will run. Total 44 member ensemble we have. That is at 2 cycles we will run the ensemble model. And then recently we made this global deterministic model into coupled, weakly coupled. The difference between weakly coupled and strongly coupled, I'm not going into detail, but the weakly coupled in briefs, in a rude way, you can say that there will have only one-way interaction. So the AC interaction is limited here. So, but then still we had the coupled medium range model, which is the 12 kilometer, which is a high resolution coupled model. The pink side on the schematic diagram is the experimental runs, where we have the 6 kilometer global model, like in a kilometer scale modeling. We now want to reduce it to 5 kilometer. It's a gray zone modeling. Then we have the regional coupled 4 kilometer over the Indian domain. That is experimentally. This gives it the regional model gives only the 72-hour forecast. That is a day 3-day forecast. And we have the operational coupled model, that is 12 kilometers. So you all may be aware of that. We have a high performance computer called Arunika that was recently commissioned, recently inaugurated by the Honorable Prime Minister. And this is having an 8.2 petaflops performance. And we have 2000 plus nodes for computational. We had that computational power. We are also having GPUs for AI/ML applications. So any students or researchers who wants to use this facility, you can approach to our head NCMRWF and you can write to us with having a problem, scientific issue, or you want to do in the modeling part. You can write and use this facility and see how the GPUs and AI/ML can be used for your studies. With that, I'll go into the talk. Like I said, that the moist convection in NWP models. So we have been talking this dry and moist convection in the past 2 days. Again, it's a kind of a recap for you all, basically. So if you look at the dry and moist convection, basically, consider this as a Rayleigh-Bernard issue problem in the atmospheric science. If you see, consider, you all may be aware of the Rayleigh-Bernard issue, that two metallic plates and the fluid between the plates, and then you heat the bottom plate and it will generate some kind of an eddies, and then after some time mixing happens and turbulent motions generates. The similar kind, you can see the similar kind of situation that happens in the dry atmosphere with the dry boundary layer. If you heat the surface is very warm or heat, kind of a desert or a dry area. The buoyant parcels raise, the warm air parcels, and then it kind of follows the temperature lapse rate and then cools. Then the cool air sinks again. So this kind of mixing happens, and then the turbulent motion generates. That is a dry convection. The classical example is the Rayleigh-Bernard. But if you introduce water vapor into that framework, dry, then the complications comes into the picture, where water has a peculiar property of phase changes and latent heat release. So the latent heat release by the water vapor that you ingested into the column can reinforce the circulation again. The feedback is where the models we struggle to represent the moist convection when you introduce the water vapor. When you introduce the water vapor, it does not follow the dry adiabat. It is the moist adiabat that the water vapor with respect to height decreases. So there are slight differences between dry and moist convection. If you want to really qualitatively, if you want to see what are the differences between dry and moist convection before going into the representation of moist convection. See, the dry convection is it's horizontal and vertical scales are comparable. Like if the eddy forms, their horizontal scale and the vertical scale are comparable. That said, their vertical motion or the upward and downward motions of the dry convection is also comparable, or they are comparable in strength. And again, the dry convection, it only helps in mixing the atmosphere. Like the real life example is that in the hot peak summer, you can see the well-mixed boundary layer and then the cumulus cloud forms. So the well-mixed boundary layer and the constant scalar quantities of theta E, moisture, temperature, that is where the mixing plays into the role of the dry convection, the dry adiabatic. So that is dry convection helps you in mixing the atmosphere. It just maintains the temperature profile. But if you look at the moist convection is, on the other hand, the ascent region occupies a very small space. Ascent regions are small, and ascent or the updrafts or downdrafts, and they are very skewed. They generate some kind of a kinetic energy when you look at the moist convection. So basically, when I say that its ascent regions are small compared to the grid, because we are talking about the modeling perspective, in the grid size, if you look at the moist convection, that size of the convection cell or the ascent region, it is very difficult for any numerical model to represent this kind of a vertical or small ascent when you compare with the grid size. So this is a numerically challenging problem to represent the moist convection in the numerical models, which we all know. Why the numerical models struggle? If you look at the cartoon here, it's a classical grid box soup dilemma. The left-hand side of the cartoon, if you see, it's an atmospheric convection in the grid box, where the convection has different flavors: turbulent motion, convection, thunderstorms, you name it, cumulus convection, whatever. So you want to taste that soup. We're asking the model to taste the soup in one gulp. The model is not able to do that. Just we are giving the model in a grid box to drink the all soup in one gulp. It's not possible. So the model tastes it and says that it's another soup. So it doesn't differentiate the flavors of the convection. So that's where the NWP, the numerical models, fail you. So this is where the parameterization comes into the picture. So we want to parameterize that particular process where the flavor, which we want to represent in the models, there you have to introduce this parameterization. When you talk about the parameterization, I just want to go pedagogical, just want to see the timeline of the parameterization scheme that has happened. So it starts with the Kuo in 1950s, where it is large-scale convergence is directly related to the convection. So that's the Kuo parameterization scheme earlier. And then later it was the adjustment schemes came into the picture, where the temperature profile and moist adiabat, the profiles are adjusted. When instability is generated in the grid box, the temperature profiles are tried to adjust and make it as neutral or stable. That's the adjustment schemes into the picture. Later, upon this, the penetrative convection schemes came into the picture, or you can say that the mass flux convection comes into the picture. I'm not going into the details, but the basic way the COO and the adjustment schemes are lagging behind when you talk about the mass flux is the COO scheme is overly relied on the moisture convergence. It just says that the convection is basically the convection intensity is directly related to the large scale convergence. In real life, in real condition, if you see the atmosphere, there may not be. I mean, sometimes there will be large convergence, but there won't be any convection. Or in other sense, without the convergence, large scale convergence, also there would be convection because of the thermal instabilities or the strong surface heating. So sometimes in some scenarios, this scheme fails. Adjustment scheme is that as soon as the model in the grid box, the instability generates, you are asking the adjustment scheme to quickly come back to your normal position, to make it neutral. So that's where the adjustment scheme fails, that it is by forcefully it adjusts the temperature profile back to the equilibrium. So the removal of the instability is quick in adjustment or maybe slow. So you're forcing the adjustment scheme. That is the way that it fails. So the mass flux schemes come into the picture. Those interested people can see the chapter 16 of atmospheric convection by Kerry manual. It is very beautiful. Then the mass flux scheme came into the picture. So what is the advantage of mass flux? It simply didn't replace the existing schemes. It actually it has bridged the gap between some of the physical gaps between the COOs and the mass flux. The gaps that it exists in the atmosphere, the mass flux scheme has tried to fix it. So what kind of issues that mass flux scheme can address or fix it? It deals the updraft, downdraft, and the environment individually or separately. And then it allows the atmosphere, the entrainment comes into the picture. The entrainment or detainment, it means it allows the grid box column to mix with the environment. So mixing between the cloud and environment happens in the mass flux scheme. And the convection evolves over time. That means, the life cycle of the convection, the mass flux. For example, in the adjustment scheme, the instability generates in the grid box, and you are trying it to remove it, and then removal by using some kind of a closure and making it neutral. There is no life cycle of convection. The trimodal convection may be adjustment schemes fails in some cases. So the mass flux scheme has this advantage of slowly showing that convective life cycle. And then it is quasi-equilibrium where the large scale convection is linked to that large scale forcing is linked to the small scale convection or grid. And then the transport of moisture and momentum happens through the plumes. Now this plume word we are hearing from past couple of days. So just want to make everyone, again, just a recap of what is the difference between the parcel and the plume. In the atmospheric sense, we generally see the parcel theory we have been studying. The parcel is a very small parcel. It's like a very one point in atmosphere having the properties of pressure, temperature, and moisture. And then it is allowed to go in the atmosphere, allowed to rise through the atmosphere when you are discussing about the parcel theory. So the changes that parcel is encountering. And the basic thing is that we assume that the parcel is insulated. We are not allowing the parcel to mix with the environment. That is the basic assumption that the parcel theory, it is a diagnostic tool only. The other hand, plume is in such a way that it has an area first. And it has the other temperature, moisture, and then you have the pressure anyways. And it evolves with height like parcel. It has the finite area. And the basic thing you are allowing plume is to mix with the environment. The plume, you are asking the plume to mix with the environment. That's how the entrainment comes into. So collectively, what we want to say is that the plumes are different plumes, or in a grid box, many plumes will give you the strengths of the convection. So if I say mass flux, that means amount of mass in the grid box or the vertical column, the plume that is changing with respect to time step is nothing but the plume velocity that the plume is raising vertically, and its area, the area that is plume is having, and the density. So if you combine all these three quantities, that's the rho and the omega and the area, is nothing but your mass flux. So This is where you can say that the parcel can become a plume if you add entrainment to the parcel, and if you allow it to mix with the environment, having and keeping the parcel a finite area in a finite area, then your parcel and plume are the same. So when I say plumes, this is a picture again I'm showing. I think most of from past 2 days we have seen this from more than 10 times. This is again the classical picture by Arakawa-Skobart in 1974, where you can see in a grid box different types of clouds at different heights, having different properties. So the main idea of the NWP scheme or the model has to collectively give the collective nature of these clouds, represent these clouds in a collective way, not an individual. It's a statistical way. We need to represent the properties of the convection. But if you look at this, if you look at the picture, each cloud has having different vertical velocity, different entrainment rate, different entrainment. So these things are all in the grid box. So we need to, now we are what we are doing, we are actually collectively, we are making it together, giving a bulk or the mean properties, the grid mean properties we are giving. Again, that is a drawback of this one, because different clouds having different properties. Ultimately, the NWP scheme has to represent this in a collective way. So now when I say want to discuss about the convective parametrization in the numerical models, especially NCMRWF model, like yesterday, Professor Adrian Tompkins he has given a very beautiful lecture on mass flux, very elaboratively. There he mentioned about the TIFR-CAM mass flux convection scheme in the ECMWF IFS system. TIFR-CAM is also a mass flux convection scheme. This unified model convection scheme is also a mass flux, but the basic difference is very subtle. Only thing is that the TIFR-CAM mass flux scheme, mainly the trigger depends on the moisture convergence. But here, the thing is that the triggering of the convection doesn't happen in the boundary layer. I mean, not happens with the moisture convergence. The Cape-based closure works in the And the basic difference between TIFR-CAM and then unified model mass flux convection scheme is that we allow the triggering part. In the convection scheme, the triggering part has been completely differentiated or segregated and give it to the boundary layer scheme. So boundary layer scheme in the model has to take care of the triggering part. So now the boundary layer has two parts. It will diagnose the convection, and then it will tell the convective scheme that this is where the parcel is ready to trigger. So I'm giving this property to you. Then the convection scheme will call based on this diagnosis, whether to call it as a shallow and deep, that will take care of the convection scheme. But the triggering is based on the boundary layer scheme. That is the difference between these two. And the convective diagnosis, like I said, it determines whether the convection is possible from the boundary layer or not. I'm not going into the detail, but if you look at this picture, so ultimately, like yesterday, if we follow the Adrian Tompkins talk, the basic term that we all need to know is the correlation between the vertical velocity and the inescalar quantity, or the convolution of that term. The vertical velocity prime into scalar quantity. So that is where the convective transport happens. So let us assume that the picture, that is a satellite image of clouds, but assume that is a grid box. Okay. Assume that is a grid box having a 10 kilometer by 10 kilometer. The grid box is having a very bright clouds. That means there are convective pockets. And then the dark patches, that is the environment. So it has both the updrafts, downdrafts, and environment in a grid box. So now what we want to do, we want to represent all these three in the mass flux scheme based on different notations. That's how you compute the mass flux, because our aim is to find out the grid mean tendencies. Now the grid has all three properties here: updraft, downdraft, and environment. We want to see how these three can be represented in the mass flux. So here you can see the red color, the V on top of the hat kind of a thing is your updraft region, and then the blue color quantities are the downdraft region, and the purple or the tilde on top of it is the environment. Now, this is mass flux. Like I said in the earlier slide, mass flux is the multiplication of density, vertical velocity, and the area. So now if you multiply all these things and then compute the amount of convective transport happening in the grid, it is the combination of the updrafts, downdrafts, and environment that has been given in this equation. It has the updrafts, it has the downdrafts, and it has the environment, which is, you know, that the total environment, total grid is, if you consider it as one, the fractional of downdraft minus updraft, and the rest of the thing is your environment. So this is where you need to compute the mass flux term. You want to compute the mass flux term, I'm introducing a quantity called M. Of course, I introduced this quantity in the previous slide, where it is the combination of the vertical velocity, the area, and the density. So those three, if you include here, the mass flux term becomes like this. Now we need to compute the grid mean tendencies. Grid mean tendencies is nothing but, you know, how much mass in a particular time step is changing if you go for another time step. That time step, the rate at which the mass is changing with respect to height is your grid mean tendency plus the source term. So the basic assumptions is that these are the very important assumptions that mass flux scheme takes into consideration. If you look the one A, I have written has a bullet points. The updraft, downdraft, and the environment regions are homogeneous, which is obvious. We have to consider that as a homogeneous regions, otherwise it will contaminate the dry updraft and downdraft. The other one is that the updraft and downdraft profiles are quasi-steady state. And then the fractional area of updraft and downdraft should be much less than the one. When I say much less than the one means the area, the grid box area. That means the area that is occupied by the downdraft or the updrafts are much less than the environment. So if you mean, then the entrainment air that is going into the plume is nothing but your grid air, that is the environmental air. That is another assumption. The last assumption D, if you see the air entrant into the plume has the grid mean properties, because the grid is occupying much larger space compared to the other two regions. The air entraining into the plume is nothing but your environmental air. So now we need to compute the mass flux term. So we need a plume model. The plume model is nothing but your schematic the picture that I have shown in the right side panel. M is your mass flux, and it is going up, and then detrainment, the mass that is going coming down from the cloud on the annual side. So if you see, when the mass is going with respect to height, it is encountering the entrainment as well as the detrainment sides from the sides of the cloud. So the changes of the mass with respect to height while during the updraft, or the change of the mass of the cloud of the plume during the detrainment, is what we need to identify. That is your grid mean tendency. The plume model is, we need to just identify the thermodynamic properties of this updraft and downdraft, and then we are good to go with the scheme. So now how do you do that? This is the algorithm of convection, where you have already the vertical mass flux, that is with respect to height, how the mass changes with respect to height when you have the environment and entrainment and detrainment. And then you have how the flux changes with respect to when you entrainment, detrainment after budget of the particular scalar quantity. If you are considering as a moisture, the updraft that is taking the moisture with respect to height can be represented in the equation 2. And finally, the equation 3 is your grid mean tendency, where you will compute the mass fluxes of updrafts and downdrafts separately along with the source term. So now this is the algorithm that runs in the model, where you have to determine the fractional entrainment rates, and then the boundary layer condition, because you're integrating with respect to height. Then you compute the updraft and downdraft source term by obtaining the profiles of updraft and downdraft. Then integrate the equation by giving the boundary conditions, and you do this, repeat this ABCD steps for the downdrafts. Substitute all these quantities here in here, then you will get the grid mean properties. Looks very simple, but it is not. So this is the algorithm that we generally, the mass flux scheme uses. Now we are ready with we had a plume. The plume has gone up and it changes its properties with respect to height. Now the question is, everything is done, but the parameterization scheme is ready. But then when I need to call the parameterization, I have the parameterization scheme, but the model has to know where and when the parameterization scheme has to be called with respect to time. So this is where in the UM, it was hard coded that UM has the 3 convection schemes. One is the shallow, the deep convection, and the middle level convection. This is a schematic diagram. the surface and the lifting condensation level. And then you have the shallow cumulus. Shallow cumulus, I'm not going into the details of the shallow cumulus or the deep convection, but the main points to be noted here is that the UM convection scheme, it does not allow deep convection over the land at night because the surface is stable. This is the assumption in the convection scheme they made, like that in the night time, assume that the land surface gets cooled because of the heat capacity, radiative cooling, lot of radiative loss. The surface will become cool. There, the deep convection won't happen during the night time. Okay. This is one kind of an assumption in the deep convection scheme when the scheme calls in the UM. The other one is that after sunset, if still instability exists, then the middle level convection trigger or the elevated convection. Let us say these two, okay. The boundary layer has diagnosed the convection, but in the around the sunset hours, instability is there in the grid box, but like if you remember, in the night time it doesn't call the deep convection, but still the instability is there. So then it starts calling the mid-level convection. It says that the instability is present, but the surface is very stable or cold. Then it is looking at the other levels. So it goes to the middle level and then it calls the mid-level convection, not at the surface. This is a very rudely I have given, but then a lot of engineering fixes has been done. This the part of the UM code. Finally, this is the convective diagnosis that boundary layer does. Looks like a snake and ladder game. Don't get confused. It is very simple. It starts here, the parcel in the surface. It calculates the buoyancy flux. The first and foremost thing that the boundary layer does when you run the model with the convective parameterization in it. So it just looks for the buoyancy flux. When the buoyancy flux reaches or is greater than 0, then it launches the parcel. And then when the parcel goes diabatically, and then it goes to and it estimates the LCL. Then the level of neutral buoyancy or the equilibrium level, then goes on, and then it checks all these things. So these are all empirical relations. There is a very I'm talking about the research PhD scholars and the researchers. This coding is all empirical. All the model codes are empirical, and there is a lot of scope to improve it or change these numbers if you are really wish to. So when you call these convective schemes, it checks all these things based on a predefined values on a particular region. So this can change with respect to region or basically standard atmosphere, this kind of condition. Otherwise, it checks all this. For example, the low level neutral buoyancy, the difference between the equilibrium level and the LCL, if it is less than 400 meters, it just goes to the shallow convection because depth is very low. So the convective flow goes to the shallow convection mode like that. So this is a part of a convective diagnosis that happens in the UM model to diagnose the convection, and then later it gives the, it will call, depend upon the convective diagnosis, it calls whether it's a deep or shallow. Now we have the plume, we have the convective parametrization equations, and we diagnose the convection, but we need to know the strength of the convection. The closure is basically what it will give you the strength of the convection. So here the closure is rapidly removes the convection instability and then makes it transport neutral. So this is the closure where we are using the Cape-based closure, but in UM we have other closures as well. Vertical velocity-based closure, relative humidity-based closure like that. But currently we are using the Cape-based closure. Here again, there is no universal closure in any convection scheme. So that's why the convection schemes, even though they're mass flux, the closures are different in TDK and this thing. So that's why the schemes are different. Now for the the UM convection scheme that we are having, I told you that is the metaphysics convection scheme having different constraints. When I just want to make sure that because most of the here participants are students, and then you may be using the WRF model as your toy model for your model simulations are running, looking at the regional evaluation of any analysis. So I just want to make sure the difference between the UM convection scheme and the widely universally used the WRF KF scheme, the Kane-Fitch. Kane-Fitch is also a mass flux convection scheme. But the basic difference between the convection scheme and the KF is that it's like I said, it is the boundary layer driven, because the buoyancy flux from the boundary layer is what drives the convection. But in KF, it is the CAPE or LFC. It's the instability based driven. And the closure is CAPE based in but here it is the stability. I think it's fast removal. In the fixed time, you will remove in the KN fridge. That is where, that's why the environment sensitive to the trimodal convection. Like I said, the convection life cycle. Initially, when I talk about the I showed that the convection growth and decay, the life cycle would be much smoother in compared to the KF. And the impact, you can see the global rainfall. I could have shown the rainfall maps of versus the WRF. Sorry for that, but assume that you have KF have a very hot pockets of rainfall, where if you look at the rainfall map, it would be much more smoother. So that's part one of my talk. If you look at part two, see, we have done all these things and we add the rainfall map, forecaster map. But evaluation of the model, whether the convective parameterization or the scheme that we are using is how good it is. That's what for the forecaster's perspective, we need to answer the public or the operational agencies. So we have to see how good the product that we are generating based on this convective parameterization scheme. So we want to evaluate the model. So while evaluating the model, we don't want to do as a normal convection skill score. That is anyway, that is there. Skill scores, computational skill score is there. But the other thing, what we are really doing here is that by applying the process-oriented diagnostics, because we want to see, because the rainfall is a process of different mixing of all process, and this is kind of an end product. But we want to see what kind of physical process that is giving whether the rainfall is good or bad, or the discrepancies in the rainfall mass between different forecasts. So how you can identify those things is based on the process-oriented diagnostics. So I'm just here listing out them different kinds of a process-oriented diagnostics. One is the convection sensitivity. Here, just bear with me. The figure shows that the area averaged forecast from the NCMRWF global model or different regions. The CEN means the Central Indian average, and the Equatorial Indian Ocean, the middle panel, and the bottom panel is your Bay of Bengal. And how I generate this figure, we have taken all the profiles during a season, and we had combined or plotted a combined histogram with the specific humidity. So you have a specific humidity as a column, and you have rainfall, another column. You just see what is the rainfall corresponding specific humidity in a 2D histogram. If you look at that, there is a classical paper by Bertherton and Holloway and Nealon. They showed that the sensitivity of the free tropospheric moisture. That is where the deep convection comes into the enhancement of deep convection happens. So that is making that as a reference. If we look at the forecasts, how the forecasts are performing in day 1 and day 3 and day 5. Equatorial Indian Ocean, pretty good, because you can see that banana type of structure in the vertical profiles of specific humidity. With the sensitivity, you can see that as the specific humidity goes from 5 gram per kg to 15 gram per kg, your rainfall is increasing. The red color is, bright color is your incremental rainfall. So the rainfall is increasing when your specific humidity is increasing, which is obvious. That kind of a bulge you can see in the Equatorial Indian Ocean, but that is not seen in the Bay of Bengal. That is not seen in the Bay of Bengal. That is in the bottom panel. You have a very thin line. That means the sensitivity, even if you have a rainfall of 0 or 2 millimeter, the specific humidity is not that much difference with the rainfall of 14 millimeters. The sensitivity has lost in the over ocean for this particular model forecast. So we thought it is maybe model is very sensitive to the boundary layer. Now we can say that the model is not sensitive to the free tropospheric moisture. Maybe it is very sensitive to the boundary layer because the triggering happens in the boundary layer. Maybe the boundary layer instabilities are acting much more faster. That is giving this kind of giving this loss in the specific humidity with respect to the height. Free tropospheric specific humidity sensitivity has been lost. This is one kind of a metric. If you look at the observations, that is the forecast. But if you look at the observations, the one on the left-hand side is the ERA file. I don't consider the ERA 5 as an observation, but if you look at the ERA 5 reanalysis and the radius onde, that is over central India, one station over central India. If you look at these two, ERA 5 could able to represent the bulge in this, this kind of a banana structure in the free troposphere level between 700 to 400. But our radius ondes that we have doesn't show anything kind of thing. It's almost all same. You can say that the surface has more, or surface instabilities are acting much more than the free troposphere to give this kind of a rainfall sensitivity with the specific humidity. This again shows that we need quality observations or radius onde ascents to really train the model, because now the AML and everything came into the picture. So the quality data that we train the model is also very much important. So we are emphasizing that the observations has to be good to validate. This is the other metrics that we do is the convective transition stats or statistics, that where we just see the column water vapor versus the precipitation. It's again the 2D association of column water vapor versus the rainfall. That means column water vapor is nothing but your theoretical precipitation. You can say that the column water vapor is your theoretical precipitation. So again, these are the three regions, different regions or Indian domain. When you look at the central India, average column water vapor from the model forecast, different colors shows the different forecast. The black one is your observed, that is from the TRMM, TMI. The red is your day 3 forecast and blue is your day 1 forecast. You look at the overland region, just ocean, all looks similar. So they are in par with the observation, that's fine. But if you look at the land region, the observation shows the very gradual increase, and then after certain one particular value around 58 or 60, you can see the sudden jump. That's where the pickup of precipitation you can say in the observations. But in the model forecast, there is no such pickup. It is simply a gradual. That means to have a 10 millimeter of rainfall, you need 60 or 58 millimeters of column water vapor to translate into rainfall in the observations. But the model doesn't need 60. It just in 40 or 48, less than 50, it can give the 10 millimeter rainfall. So model is either entrainment is too high, or it is giving light rainfall too frequently. That could be one reason. So this is how we need to find out the shortcomings in the model forecast by applying the process-oriented diagnostics. The other one is that we do the process-oriented diagnostics. Another one is that the radiation versus the moist static energy anomalies. That means you bin the radiation term with respect to the total net radiation with respect to moist static energy anomalies. It's basically says that the association gives you the radiation color-related feedback mechanism. The good the association, the cloud-related feedback mechanism in the model. If you look at some of the active conditions where the expect that the cloud-related feedback mechanism should be good, you can see the model forecast in day 3 and day 5. Different colors is day 3 and day 5. You can see a lot of spread here. So one can say that the model has also shortcomings in the cloud-related feedback mechanism. I'm just listing out what kind of a process-oriented diagnosis that we can see to identify the shortcomings in the model forecast. The other most powerful tool is moist static energy budget. This, I think you have yesterday, someone was talking about the moist static energy, so I don't go into details. But when we apply the moist static energy to the medium range forecast, there are regions where you have the association, like, different color bars, different legends in the graph shows the different terms of this equation. The purple is your horizontal advection of moist static energy, and then moisture, temperature, and then the vertical advection of moist static energy, then the adiabatic terms. So if you look at the precipitation, that is orange, it is in association with the, actually that should leading the precipitation is leading the moist static energy. Or you can say that this is for break and this is for active condition. When you have break that is happening at the day 0, your moisture is leading nearly 2 weeks before the dry advection is coming towards the region 2 weeks before. But this association in the active you don't see that association, because if you carefully observe that orange curve, that is in the orange, this is the rainfall, but the red curve is your advection of moisture. The moisture doesn't show any that kind of an indication. In general, in the moisture static energy budget, the leading term would be the horizontal advection of moisture, where the moisture comes into the area and it drives kind of a circulation, and then it will give the rainfall. The vertical transport happens. So in this time scale, the model is not able to show this kind of a leading precursors. So again, this is another shortcoming in the model, that model is not able to show the active conditions good compared to the break. This is another POD that we are doing, the Plume-by-Anstey framework. I'm just skipping this one. This is just to give you. Now we have the model, we have the output, we know how to evaluate the model, but our ultimate aim is to, how do I translate these PODs into the operational? How do I translate this into a common man or the society, where I can convert this research that we are doing into operational purpose? So that's how this R2O comes into picture, research to operations. One example I will giving you, we need to, whatever the model improvement, whatever the model forecast or products that we are generating has to be translated into the common man for the better forecast. That's the main idea. So how to translate it? So one such thing is that this, we recently were working on one new algorithm called GDI, that's a Galvez-Davison index. It is an empirical formula, but it has a very strong basis on theta E. It works with the theta E function. Then what we identified is that even if some conditions, if the rainfall forecast is not good, GDI can give you the better forecast. So in a continuous way of improving and step towards improving the model product. So this is one such kind of a product where you can use this as a pseudo rainfall, where your model forecast may fail in the rainfall, but since it is considering theta E moisture parameters up to the free troposphere, this is giving a good forecast compared to the rainfall. For example, if you see, there is a case, there are false alarms too. I mean, I'm not saying that the GDI is the solution for better forecast. There is an event that has happened in the 19th July 2024, where you can see a large MTC kind of a circulation over Indian region. That if you look at the rainfall from the forecast, this is day 3 rainfall, not day 1. Day 1 is okay. But in the medium range model, I just want to see the 72-hour forecast, which is valid on that day. So if you look at the 72-hour forecast, which is valid on 19th July, the rainfall forecast from the NCM is not that good, because this patch of deep convective cell is completely missed in the rainfall. But if you compute GDI, could able to see that kind of a cell. That is happening in the coast of Gujarat or somewhere. It is the GDI able to pick that, because GDI is having a moisture temperature into the theta E into the equation, where it's a pretty good, like it has the structures. It represents all the kind of a tilted rainfall band, and then you have the equatorial convection. Pretty good it represented. But where the rainfall, this northwestern part of rainfall has been completely vanished in day 3. This could be because the model climatology, the model knows that the northwestern part of India is dry, would be dry in the monsoon season. So the model may be giving a rainfall, it's saying that in day 3, the rainfall may be evaporated or not giving that kind of a precipitation, what we need to be, or what should need to be compared to the observation. So what I want to say is that there are some kind of a products where you can improve the forecast and translate this PODs into operational by applying some kind of a techniques. Or this is one such kind of an algorithm where you can use it as a pseudo rainfall. That's all for the talk. After that, I will do some kind of a lab exercise, and thanks for your attention. I'm ready for the questions.
Do we have any question before we go to?
Yeah. So in the MSc thing, you showed that the horizontal advection of MSc does not show any kind of lead lag, right? So in your model, have you seen that probably does the propagation of the system, let's say BSIs or anything, those things are okay? I mean, usually, if you look into some previous literature, people talk about the propagation or maintenance of the BSIs or type of disturbance are kind of modulated by the horizontal advection of MSc or something like that. So does your model get the propagation right, but it's not getting the lead lag right or something?
I think this is a medium range model. So we give the initial condition, it gives the 10-day forecast. And again, we give this initial condition second day and gives the 10-day forecast. So the forecast is not, it's a cyclic forecast.
Okay.
Okay. So one initial condition, if I do after 11th day, then I can see the 10 day. But then, BSIS, I can't see with this model.
So you mean your lead
This
time is shorter than the...
Yeah, this is the composite picture, just to give a glimpse that some parts of the thermodynamics, it is missing. I just want to give you this. BSIS, I can't really see with the medium range model.
Okay. Yeah, and I had another question that in that precipitation pickup that you showed in the land, this one. So, and also in the previous one, you were saying that, here, the previous one, yeah. So you said for some region, the mid-tropospheric moistening was not, the model was not getting right or something like that, right?
Yeah.
So do you think these two are related? I mean, let's say the reason convection is sensitive to mid-tropospheric moisture is sometimes because the boundary layer quasi-equilibrium, that the cold, the convective downdraft sometimes bring MSC, and you need to balance that with surface fluxes. And can that be that due to maybe some of the region, your model is overestimating the mid-tropospheric moisture? That's why, again, that's translating back as a higher column water. I mean, have you looked into that or something like that?
First of all, these two metrics that I'm showing, that's convective stats, and then this one are more or less kind of similar, because this is the vertical distribution of moisture. I want to see where the moisture is peaking at which level it is. But this one is just integration of Q.
Yes.
It is just, so both are way related. But then here, what I'm saying is that the sensitivity is lost in the Bay of Bengal, because it maybe the boundary layer is acting, but I don't know whether it is overestimated somewhere, because all the three regions I selected because in the monsoon time, these are the three mutually interacting regions where you have a largest heat sources are available, like in the Bay of Bengal or Equatorial University in Central India. So that's why I selected regions. All the three regions except land, they are pretty good. The other regions, land, it is having a different. I didn't show you that there is one more thing, that in the UM has a systematic land dry bias over land, like in CFS V2. Even UM is having a dry bias over land. So we made some experiment study that giving 100% irrigation to that surface, and we want to see how the moisture is going up. But even then, the model is not able to show that saturation, and still the dry bias persists. So, that's unsolved problem. The dry bias, the reduction in the dry bias has to be.
Hi, thank you for the talk. So I wanted to ask a related bloom model. So I'm assuming that when you are calculating the mass flux of the entrainment, so you are taking it, the area is to be constant, right? You are taking a control volume and just. So have you tried to look at the area of the plume, because it will eventually convert into a fractal kind of area, like lot of areas. And again, this kind of model, like it's always assuming that the plume heads are always increasing, right? But when the latent heat is produced, so it produces the additional buoyancy. It just throws the plume up. During that time, there is a lot of necking in that area.
No, this model doesn't assume that the plume is always go on increasing. I didn't say that the plume is go on increasing in the model. It's a the UM convection schemes runs in such a way that it takes each grid box as a single column model, and then it communicates with this other model, okay, other column, okay, other grid. So the plume in that grid box is doesn't rise. It has its own properties based on the temperature and the environment, downdraft and updraft. The plume changes its mass flux with respect to height. It doesn't assume that it go on increasing. I don't know whether I answered your question or not.
Okay, so
Yeah, if you feel that your question is turning into a discussion, then just limit your curiosity till the coffee break. So I'll just give the mic to. Oh, okay.
Hello, sir. It is being seen that the model is giving better result over ocean compared to land.
Yeah.
So, and you said that triggering of convection is depends on the boundary layer. Are you not thinking that we need also need a better parameterization scheme for boundary layer also to properly represent it?
Of course, of course.
Uh.
In model, I didn't say there's one more component, the land surface. The land surface also plays that here in the UAM, it's called Jules. Jules is a land surface scheme. The land surface scheme also plays a very much important role because the canopy, the evapotranspiration that happens in the model is also helps in computing the triggering the convection by calculating the buoyancy flux. So yeah, there are scope in any like every parameterization, like I talked about the convection. Even boundary layer has the scope in implementing the in improvement. So if you have the better coupling between the land surface and the boundary layer, the coupling between the land and then you will have a better representation of convective diagnosis. That is there. Yeah.
Thank you.
Hi. So in a slide you had showed about the convection is the scheme does not like shuts off in the night time or something. Night time. So if in case there is a dynamical system, say for example, a cyclone which has made landfall and it's over the night time. So in that time, cyclones do have deep convection irrespective of whether the surface is hot or not. So what parameterization, like how does the model take care in that if that statement is?
This is the model that I am talking about is the atmospheric only model. We had the coupled model right now. It has all the coupling process happens, but then your point is valid. That is why, it is a propagating system. It is not generating by computing the buoyancy flux. Okay, when the cyclone made the landfall during the night, what happens to the convection, right? It is tracking the convection. Sometimes the model gives large errors for landfall, landfall timing or the landfall region. That also happens in the model because of this kind of an assumption. What I'm saying is that these kind of assumptions exist in the model, needs an improvement.
Do we have any other question?
Regarding this cloud you showed, sometime the cloud it shows it moves vertically to some extent to the stratosphere. In between, if middle troposphere the cloud breaks again, there is a patch of cloud over the high altitude. So what kind of effects it gives to the land? I mean the rain, how much, what kind of precipitation we can get?
If the cloud is continuous,
It's I repeat the question again. And
I understood. If let us say there is a
Cap.
strong entrainment of dry air here,
yeah,
and then what happens is, I don't think the rainfall comes from this part if the entrainment is there, because it's ice part. I don't think the cloud becomes when it's shallow, right? The shallow convection, or the cloud is break. I mean, most of the cloud part that is here, that is evaporated. It's because it is mixing with the environment or the dry air. The other part only gives the rainfall. So the amount of column water vapor in that part is translated into rainfall by the model. So it may be less, but if you goes continuously the deep, then your column water vapor increases, then your rainfall amount will increase.
thank you.
Thanks, Mohan. So my question is about that index, GDI.
Oh, yeah.
And so I saw that in the map, part of the rainfall was successfully captured by parent model, whereas part over Gujarat was totally missed, which GDI captured. But GDI missed some of the rainfall that was captured by income. So I'm kind of a bit puzzled as to what went on.
Yeah. Let us say this is what I'm saying.
Orissa or Telangana,
Yeah.
that red blob of 50 millimeter and above was kind of,
this is an index where you had an indication that potential rainfall zone it is showing that it is not exact, but in this case it is completely absent. You have a GDI, but then again this is a thermodynamic index. This GDI is completely a thermodynamic index.
yes, it also has lots of false alarm, I felt, in GDI, whereas your parent model maybe it doesn't have it as much. So I was thinking ultimately you would want to supplement GDI information to your forecasted
rainfall. So we don't discard the rainfall forecast to the decision support system, but we will say that along with this you look this also. When you give the decision support, why don't you use this also as a supplement and see. Now you use forecast of persistence, and then it's kind of a thing. So GDI is one such kind of a product, but needs improvement. This is this is only thermodynamic.
I want to think of a way of merging.
Yeah, we're doing some kind of a dynamical aspect. She's good in GDI.
Machine learning, right? I thought.
Machine learning would be another good idea to train the model, but then we need
these two. Yes.
Yeah.
Thanks.
Yeah.
I actually had similar concerns with GDI because the birth of GDI is from the motivation to communicate it with people, I think, from the user end of points, so that you have something. And you cooked up GDI using few, like 3-4 thermodynamical variables. So I think it would be an important point to communicate the thought behind GDI, so that from a user point of view, they know what they're using, or like user in the sense people take decision. Because rainfall is much more easier to relate to.
Than GDI. Yeah, I understood. And then again, this GDI is, like I said, it's only thermodynamic. Now we want to include the dynamical parameters as well for the modeling part. Look at the omega at 500 hectopascal or the convergence at the low level, and it's not only looking at the rainfall. We are looking at the other factors that will help or affect the rainfall. Make a regression equation and find out what is happening in GDI, a modified version of it.
So now we can go to the lab part.
Yeah.
Just before going to the lab part, I just, from student point of view, like the decision tree that Mohan shared, I think that's a very good way of seeing how a model works, because we read papers, and based on those papers, people like Mohan code the model, and then when they code it, then there are very rigid demarcations like 400 MB to 600 MB, a yes and no type of tree. So it's like if something happens in 350 MB, then that's missed by the 400 MB. Whereas physics-wise, that might be relevant, but still it missed because of it's like a yes and no type of rigid thresholds. So that is something I think you can just, because these videos will be recorded, you can just go back and see the tree and feel like how a model works.
At least a supplement to at least that flow chart, some part you write your own code in Python or whichever language you just check, put your own data and see whether it is really making with the real atmosphere or not, that kind of thing. Yeah, the final part would be just a hands-on exercise. Not much, like Vidyut has yesterday he has given very elaborately from step by step. This is not like that. You have a Python, a notebook in the QR code. You just scan it, and then you will see a Python. It is opening to a drive. Yes, it's not.
This should take you to Mohan's drive.
Yeah.
And then that drive and its contents are all like shared to anyone with a link. You can view it. And then probably there is a Jupyter notebook, which you can again make a copy of, like you did yesterday.
Yeah, I mean, like if everyone has, I think you're able to access my drive, everyone? Yes, right? So this is the event, then the drive, I think you can see a Python notebook, and then you have text files. July 4, 2020, you have 2 text files, and the regional model, you have a SKUT of 12 UTC and 0 UTC text files. So there is a 4 + 2, 6 text files with a program called Model Convective Diagnosis. Python Jupyter, yeah.
Just I noticed that Yashas and Shreyas, probably two students have unknowingly made a copy of
Okay.
your script
Because
on your drive.
Yeah, because I gave the editing permission to anyone having the link.
Yes, but I think we can request participants. They are pretty smart, so we can tell them not to do this.
Yeah,
So
when
that
you,
your
when you
drive is
create a
not full.
copy.
Yeah, don't write in my drive. Maybe you can copy all these things in your place and then do it.
I mean, Mohan created this drive for the tutorial purpose, so you were not doing anything very like, yeah, but still it is suggested that you create in your own
Just
drive.
copy, or you can copy everything and then you can do it in your
only
workplace.
possible disaster is Mohan gonna delete this, and then you will lose all the edits that you would do for it.
Okay. So this is okay. Before going into this, I just want to. Initially, I was planning to do the TIFR-CAM analysis, and I want to bring the charts. That is old meteorological charts. I don't know how many of you know that TIFR-CAM charts. I was want to make a copy of the charts and give some groups and do it, but it didn't happen. I didn't get that original chart to make a copy. So this is kind of a TIFR-CAM. You'll see the TIFR-CAM. The Python code will plot a TIFR-CAM of particular event that is happened on 4 July 2020 over Mumbai. This is that day IMD has issued a red alert over Mumbai, which is having more than 200 millimeters of rainfall. Like yesterday, Bangalore event. This is a Mumbai event, you can see. So this is that event, which has this picture I just showed you that it is a very high rainfall peak. It is going up to 240 millimeters in the observations. This is the regional forecast of particular that event in regional forecast on 4th July, along with the observations. The dotted circles are the automatic rain gauge stations that is in the Mumbai municipality region, MCM. So those stations has reported rainfall up to 150-200 millimeters, and the model in day one forecast is pretty good, although the patch is larger, but the large scale. But then the regional model is able to show in day one forecast, but day three, you can see even though the rainfall is much, the day 3 the rainfall is not there. I mean day 3 forecast that is valid on July 4th is not able to show in the regional forecast. We will do some kind of a analysis of this event. So this event you can find out in the Google Drive. Nothing much has to do. Just you copy all these things, try to run the code by each block. If you are okay with that, I don't think you are familiar with the Python Jupyter notebooks, right? Everyone nowadays. So just this is I installed this matpy in my thing. So you just run each block, and then it will guide you one by one. You can do it the blocks, and you can run in the Jupyter, and then let me know where you are stuck. Here, one thing you can do that when it asks for the import files or upload files, the below code is taking 3 files. One is July 4th, 2020, 00 UTC, TXT, that is observation. And then you have a day 1 of 0 UTC, and again, day 3, the below code. There is one more block here, day 3. So you need to import these 3 files, day 1, day 3 from the model, which is having a 00 UTC cycle. along with the observations. And here, 0, and then the 0, and then day 3 is 0.
Okay, I have just one concern. These files, are they loading or giving an error?
What was it?
Okay, so the script is in your local drive, and the file is in your
In my drive. Okay.
So if this file is not big, then maybe you can just quickly.
Those are very small KBs. It's a text.
Yeah, it's a text file.
Since
there
you
are
are all can access my drive, can you download the file? The text
those-
files. The
those
text
TXT
files. Yeah, these text files. These 6 text files, 4 from the model and the 2 from the observation of 00 UTC and 12 UTC. If you could able to download, just download and keep it in your place, and then while it is asking for the upload, you can give your path. Yeah. Yeah, it doesn't have much, I mean, like, it's a small folder you can download. Let me know once you download and run this. What happened? Somebody has completely simply moved, I think.
All files are gone now. Somebody has stolen Mohan's files. Surrender who have done it.
Raise your hand and then the lab is done.
Okay, I just. Oh yes, that's a good point. I think most of you have copy of this folder.
No, if you, yeah, even if it is deleted from my drive, it is fine, but you made a copy, right? Yeah. That's okay. You just run from your side and show me what you got.
And then after that, you pass over the rights so that then you make it.
Edit, just a viewer, yeah. Restricted to myself. No, even Vidyut was saying that, before giving the editor permission, just give the viewer so that they can make a copy. I was so, liberal that I should give the editor. Yeah. Easy, yeah. Okay. I think that is fine. I think no, they can't do. I just change the permissions. Okay. Yeah, if you copy the code in your local area, just run and let me know what you got. Blockwise. Yeah, because I have edited the permission. That's okay, fine. You just leave this one. This is fine. These files are, temporary files. Just concentrate on, running the code. The first one. Check the file name. No. Has anybody got this 3-panel plot? This is a panel plot. Be able to do? Here the plot. Anybody with the 00 UTC files imported, or the input files as 00 UTC and had this? This is 12 UTC. 00 UTC files I showed you. At this kind of a plot, would you be able to generate this kind of a plot with 00 UTC? No one. First one is not coming. Yeah, it's supposed to make 3 plots. Yeah, there are 3 places you need to change the time. This is 0 UTC, right? Yeah. Go up. The input files. Come down. Here. 0, and then you have the 12 UTC file, right? These are all files you are importing, right? Go up. And this is come down. Come. No, this is no. Yeah. This is 0 UTC, 0 UTC, right? Come down. There are 3 places you file. No, just a second. Here 0 UTC, 1 file. Okay. This is 0 UTC. 0 UTC, yeah, you should get all. Yeah, but there was some error. Attribute side. Not do this kind of matter. Oh, yeah. It should not come like that. Because I have checked the data. Somebody, yeah. You'd be able to, can you show me? This is 12 UTC, right? Okay. Able to. Yeah, how many of you got this kind of a plot for 12 UTC? Only one. Grade 12 or 0. Yeah, I mean, like if some people have done and some, I think most of them has not been.
The file name, there is some change in that. So it is like 00 UTC in the file. So you need to change that to 12 UTC. Then you can run all those codes and you will get it.
Supposed to generate 0 UTC and then 12 UTC. Total 6 plots, 2 sub. But it is only working. That is
In 4, 5, and 6 cell, you can change that to 12 UTC. The name of the file actually.
no, you can,
Here it is
no, this is for 12 UTC. The same plot can be generated with using the 0 UTC. That's why I gave you 6 files. 3 files for the 0 UTC, 3 files for the 12 UTC.
We are only getting
Observation, you are not able to. Somebody has to, I think the original file.
no. Actually, I downloaded the whole there
Fol-
it was not-
folder?
Yeah,
Okay.
I downloaded.
Then
the
it, you
whole-
could. Let us do the 12 UTC then.
Yeah, let's.
If 12 UTC is working, just do the 12 UTC. Can we continue? Okay. Yeah. Okay, I'll just hypothetically say that the 0 UTC, the event has occurred around the early hours of 4th July 2020. So when you look at the 0 UTC sounding from the observations over Mumbai, you had a very high cape, like like you are seeing in the panel 2, the middle panel, kind of a plot is there with the 0 UTC. All the forecasts, the observed sound day. But if you do the same thing with the 12 UTC, the first one is the observed radius on day, TIFR-CAM, and then the day 1 forecast and day 3 forecast from the regional model. Can you tell me the difference between these 3? These 2 are the forecast, that is the observation. What are the main differences that you have seen here? Cape is almost negligible in the observation. But in the model forecast, you have cape of nearly 10 times. It's 2370 joules, and this is 2017. This is observations. This is model. And in day 3, it is again 2000, close to. Day 1. Day 3. nearly 10 times. So if I am a forecaster, I am issuing the forecast over Mumbai region as a nowcasting. If I take this as my, the model forecast, if I take this QT diagram or the TIFR diagram, if I see this one, day 1 and day 3 forecast, I'm missing everything, right? I'm issuing a red alert because my Cape is very high. The observer is nothing is there. So in the QT diagram, by looking at this positive area, if I use this as a nowcasting tool along with the others, if I use this as a nowcasting tool, the model is not able to show that positive, not able to release the Cape. It is still maintaining that Cape. Okay. So what could be the reasons in the model? What can you list out what could be the main difference that model is showing a higher Cape compared to the observations? Can anybody list 1 or 2 points? What could be the models where the model failed in showing? If the model is representing a large Cape, what could be that thing? Because if you look at the Cape formula, it is the buoyancy, the temperature difference between the environment and the parcel with respect to height, and you integrate it. So where could be the model is failing? Why it is giving a huge Cape? Yeah, we just list out one. Cold free troposphere. Yeah. Anyone else? Any other reason? Cold free troposphere, or you can say that the less entrainment. Less entrainment. Yeah.
I was looking at these 3 plots and I saw this red curve, which is environment, and the black curve, the two moist area band. And the area between the two is peak.
Yep.
And which is overestimated margin. So either the red curve is wrong or the black curve is wrong. Was my initial.
Yeah.
And
So
maybe there are other reasons why.
what could be the other reasons that model can fail, giving the large Cape? I'm telling this is a Cape based on the parcel theory. I'm giving you a hint that it is a parcel theory. The parcel starts from the surface, right? Let us say I have 2 parcels in the surface, the parcel 1 and parcel 2 having temperature T1 and T2, where my temperature increasing on x-axis. This parcel is warmer than this one, right? As per the parcel theory, you have a warmer parcel, you will have a high Cape because it's the buoyancy, right? The warmer parcel along with the moisture anyway. Classes Clapeyron, since you have a warm temperature, you assume that it is a moisture. So the parcel that is on the right side of the P1 will have the larger Cape. So the larger Cape that we see in the model may be because of the warm bias in the model. Can I say that the surface is much warmer? The model surface is much warmer than expected. So the warm surface, or you can say the warm bias, right, associated with that more moisture. Anything here? Need a mic.
So sometimes Cape calculation is based on parcels that come from a different model level as well, right? So for example, parcel can start from the surface, or there is a Cape calculation based on the mixed layer parcel mean properties. So
Yeah.
that can change the Cape value as well. So
Here in this code, the cape is computed based on the lowest parcel, lowest
Okay.
surface parcel. All the observation, the model is taken from the lowest parcel. But you made a point that the vertical resolution, model vertical resolution. Model
Yeah,
vertical
model.
resolution is in different levels where the radius on the verticals are different.
Yeah, vertical resolution is one thing, but in observations, people usually also consider mixed layer cape.
Yeah, I mean, if you
A
want
cape
to,
calculated based on the parcel that has a mixed layer property,
Yeah,
rather than only the surface where it can go to extreme.
cape has several, if you want to calculate the most unstable cape,
Yeah,
you
most
take the
unstable.
most unstable cape is your 100 millibar or 100 meters. But if a simple cape, surface-based cape, this is surface-based cape.
Okay, okay,
So I'm not talking about the MU,
okay.
but even if you consider MU, all three are having the same thing. But
Okay.
here, this is surface-based cape.
Okay, okay.
Again, the cape computation, right? Or any other modeling point of view? Maybe the previous time step, the cape is there, the model not able to consume everything, it still retains. The next time step, it is still giving the cape instability the model is having. It is not able to, you can say the convective memory.
Can then be a reason because of the like
Convective
maybe
memory or
inversion,
model. Yeah.
inversion or something like that's too strong, maybe in the previous time steps in the model.
Yeah.
That's
So
making the accumulation of moist static energy more, and then suddenly it's realized.
yeah, this could be model thing. So now by looking at one plot, we just find out this many number of discrepancies in model forecast. So, it is very difficult. It's a challenging that to fine tune a model based on which physical component is really affected this kind of a thing. So what I want to, the exercise, the main motto of this exercise is to find out the physical process that is giving this kind of an error. So now if you segregate these things into different things, land surface could be an issue, the free troposphere could be an issue, the partial origin, that could be an issue. So there are several ways that you can improve it. We are fine tuning it. Well, down the line, maybe we will improve the model, but still we are at the same stage in identifying the errors.
Yeah, one more observation is that the direction of wind with height in the observation, there's a change at around some mid-level.
Warm air advection, that's, when the clockwise rotation of the winds with respect to height gives the warm air kind
but the model panel plot number 2 has that kind of westerly going up to a even more higher levels. If you see the panel plot, not this one, right?
Someone is using my drive.
Yeah, this is not the plot actually. Yeah.
That is.
So in the observations, the westerlies were limited only to a lower levels, but in the model, it was a little more higher as well.
It is just to show the hodograph kind of a thing. So I'll stop here. This is the exercise is meant to show that the model forecast can be wrong in many times. So you should be prepared for that. And then we had a lot of scope to improvement. And then whatever the research that we are doing has to translate to the operational purpose. Thank you.
Okay, let us think. You already